The Aldol reaction is important because it allows for the joining of carbon chains. In this instance, we get two equivalents of an aldehyde or ketone joined together with a double bond. Now what I'm going to do is show you the mechanism for this, and then I'll use an example. Alright, here we go. So we're going to use two equivalents of this aldehyde, and we're going to use sodium hydroxide and water, and the product we end up with will be an alpha beta unsaturated aldehyde. Alright, so let's look at the mechanism. In the first step, OH minus comes in and takes an alpha hydrogen of one of the aldehydes. Now with the alpha hydrogen we know that one is acidic because the anion is stabilized by resonance with the adjacent carbonyl group. Remember that we can't take a proton from here or here because that anion will not be stabilized by this carbonyl group. Then we can have the negative charge attack the other equivalent of aldehyde. And that's where the two carbon chains join together. Alright, so now we've got this anion here which can take a proton off water. Now at this point we've got a compound that's got an aldehyde group and an alcohol group, or an aldol. That's where the name of the reaction comes from. But this is only an intermediate. We can't isolate this compound. What happens is the OH minus will come in and take this hydrogen off and form a double bond with the removal of the other OH group. So what we end up with is this. And we get H2O and OH minus as well. Now the reason that this next step happens is for a couple of reasons. The first one is this proton is somewhat acidic, so it's already prone to removal by an OH minus because it's right next to a C double bond O. Now the other thing is that we're forming a double bond that's conjugated with a C double bond O, and the double bonds formed in these reactions also tend to be pretty substituted as well, which makes them more stable. So all of that conspires to lead to these double bond compounds with the C double bond O. So alpha beta unsaturated carbonyl compounds are what we usually end up with here. Now that's not the only product that's possible. The other product we can get is that if we take the H and we rotate it over here and put this group over here, we'll end up with another compound. So we're going to get cis and trans isomers as products. Now you'll notice that up here I didn't show that. What I showed was these squiggly lines, and these squiggly lines indicate that cis and trans isomerism is possible. Cis and trans isomerism will be possible only when each carbon atom has two different things attached to it. Each carbon atom from the double bond has two different things attached to it. If either carbon of the double bond has the same thing attached to it, then we don't get cis and trans isomerism. I'll show you some examples of that a little bit later. But rather than drawing out both cis and trans isomers, it's easier just to go ahead and put the squiggly lines in. Now when you put the squiggly lines in, you can either put them on the bottom ones or you can put them on the top ones. It doesn't really matter. Now what you'll notice here is that we have an easy pattern that we can use in order to get an aldol product. So you can see that if we did this and showed the alpha hydrogens, and then showed the reaction with the aldehyde 1, 2, 3, 4, then what we would see is that we were losing H, H and O, which is water, and then joining these two groups together. And because we've got different things attached to both carbons from the double bond, then that means that we are going to get cis and trans isomerism. So that's how you can do it, how you can figure out what the product will be without doing the mechanism.